name is Matt Ratanapanichkich, and I am one of the GSC co-chairs for the 23-24 academic year. Thank you all for being here to celebrate the first of 2 annual Everhart lectures. At the GSC, the Academics Committee hosts events recognizing academic excellence at Caltech, with particular importance given to the Everhart Lecture Series hosted in collaboration with the Graduate Office. These lectures recognize 2 graduate students for their outstanding ability to communicate cutting-edge research to a general audience. For our first lecture, we are proud to select Keefe Mitman, a newly minted PhD from PMA. But before I hand off the mic to Keefe's advisor for a more personal introduction, please note that we will have the second lecture in the series on June 10th at 4 p.m. in the same room. But with that, here is Keefe's advisor, Professor Saul Tucholsky.
So Keefe was an undergraduate at Columbia, and when I read his application to Caltech, I saw that virtually all his undergraduate research was in experimental particle physics. But I noticed that he had also taken 3 graduate courses in quantum field theory. So I thought, maybe there's some hope for him anyway. So when he came to Caltech, we recruited him into our group. Our group works a lot on solving Einstein's equations on the biggest computers we can find. And at that time, we had just developed a new algorithm, a new way of solving Einstein's equations. And I said to Keefe, we have this new technique. Why don't you see what you can do with it? You know, maybe there's some interesting applications. That was 4.5 years ago. And I don't think I've given him any guidance since then. He just somehow, went off and did his thing. And we, in fact, just in the last hour, we got the news that he's been awarded a Robert F. Christie Prize for an outstanding thesis in theoretical physics. So, congratulations to Keefe. And he's going to tell you all about what he's been doing here.
Great. Okay. Well, thank you very much, Saul, for that very kind introduction, and thank you to the organizers of this event for inviting me to speak here today. Before I begin, though, I'll actually need a couple of volunteers from the audience. And although this may seem daunting, all you have to do is say a number. So can I have 1 volunteer? All you need to do is pick a number between 1 and 8. Yes? 3. Okay. Give me 1 moment. Okay, 3. Can I have a second volunteer? Oh, sorry, I'm going to pick the person right there. Can you pick a number between -0.8 and 0.8? 0.7, okay. And sorry, yeah, go ahead. The same number between -0.8 and 0.8. 0.5, okay. Let me make sure that looks okay. All right, so there will be some magic going on in the background. You don't have to worry about what exactly is being performed right now, but it will become relevant towards the end of this talk. So with that out of the way, we can now delve into the nitty-gritty of this talk, which really concerns Einstein's theory of general relativity. Now, Einstein's theory of general relativity is a theory we use to describe the force of gravity within our universe. And what's particularly useful about Einstein's insight is he realized that if you're to describe the interaction of gravity, you really need to construct this 4-dimensional space-time, which combines the spatial dimensions and the temporal dimension into a single fabric. With this notion, you can then derive what are called Einstein's field equations, which I've written in their most simple form here. And you don't really need to understand the complex mathematics that's embedded within this equation. You can instead simply focus on what each of these terms corresponds to. So on the left-hand side of this equation, we have what's called the Einstein tensor. And effectively, all this corresponds to is the way in which this space-time fabric is warped. Namely, as you can see here, this space-time has some non-trivial curvature, namely it's not exactly flat. And this quantity here describes exactly that curvature. The term on the right-hand side is what we call the stress energy tensor. And this corresponds to the presence of mass and energy within your spacetime. And so when you equate these two terms through Einstein's equations, what Einstein's theory says is that the presence of mass or energy within your spacetime will warp that spacetime fabric and give rise to curvature, which is the notion of gravity that we're very familiar with through our everyday interactions. And so effectively what this warping of the spacetime fabric tells us is that if you were to consider the trajectory of a single object within this spacetime, such as the Earth orbiting around the sun, the Earth wants to follow the straightest path possible. And so when you place the Earth within this curved geometry, it turns out that the straightest path actually warps around the sun following this curvature, which gives rise to our orbit within our solar system. But the picture I've shown here is purely static. Namely, the Earth is not actually moving around the sun, and so you don't see any dynamics within the spacetime curvature. But another important prediction of Einstein's theory of general relativity is that if I were to imagine these two bodies in motion, then as they move around one another, they should also change the fabric in some dynamical way. And so this actually gives rise to a very interesting phenomena known as gravitational waves. So here I'm showing an example of what the spacetime fabric warping might be for two massive objects, say 2 neutron stars or 2 black holes, that are orbiting around one another. So here you can see that as these two objects move around, they warp the spacetime curvature, and that warping actually propagates outward in the form of a wave. And this wave is what we call a gravitational wave. Now, because this warping of the spacetime fabric simply corresponds to how much the space and the time is being expanded or contracted, what this means is that as this gravitational wave is propagating outward, say from outer space to us in this room, it's warping the spacetime by making it expand and contract as it propagates through the universe. And so it turns out that if you work through the mathematics of these gravitational waves, they're only allowed to change the spacetime in specific ways. And the ways it changes the spacetime are through what we call polarizations. So there's two types of polarizations. The first one is called the plus polarization. And what it says is that if the gravitational wave were passing through this room perpendicular to us, it would cause the spacetime to expand and contract in a plus-like manner. Similarly, we also have what's called the cross polarization, which is effectively equivalent to the plus-like polarization, but is simply rotated by 45 degrees. Now, part of the reason why we care about gravitational waves in physics is that, unlike light, which might be blocked by some massive object, because gravitational waves correspond to this ripple in the nature of our reality, namely these ripples in the fabric of spacetime, this information can actually propagate through massive objects. And so what this means is that if there's some kind of astrophysical event in outer space that sources these gravitational waves, even if there's a massive object in front of that event relative to our line of sight, like some massive star, the gravitational waves can still propagate through that object, whereas some light-like particle wouldn't be able to. And so this gives rise to the field of gravitational wave astronomy, which lets us view our universe with a new type of lens, namely the lens of gravitational waves. But I'm actually interested in gravitational waves for a different reason. And the reason why I'm interested in gravitational waves is because when these objects are sourced by some kind of massive binary merger, such as the stars shown here, you can see that the gravitational waves are actually sourced in this regime of the spacetime where the curvature is most intense. Namely, the curvature of the spacetime here is much more significant than it is farther away from the source. And because of this, as these gravitational waves propagate outward, they actually carry information about the curvature of the spacetime near these massive objects. And so the reason why this is important is because in physics, our job is simply to come up with theories that seem to explain our everyday phenomena. But there's no inherent reason why Einstein's theory of relativity has to be the correct theory that describes gravity within our universe. It could certainly be something very similar to Einstein's theory, but there's no reason it has to be exactly Einstein's theory. And so it turns out, actually, that if you kind of study physics long enough, you realize that Einstein's theory has to be wrong at some point, because it's inconsistent with the physics we use to describe the microscopic realm, namely that of quantum mechanics. And so the hope is that if we observe gravitational waves being sourced by these massive objects with massive amounts of energy, there's some reason to believe that perhaps signatures of the theory of quantum gravity might impart themselves on these gravitational waves, which we could then detect here on Earth. Or even classically, it might just be that Einstein's theory simply isn't correct, and that if you probe this regime of strong curvature of intense energy, you might realize how Einstein's theory is wrong, and this will give us a better understanding of the way in which our universe actually works. Okay, so this is kind of the motivation behind why we study gravitational waves and why we aim to detect them here on Earth. But now the question is, well, how do we actually go about observing such an effect? For this, we have some very advanced detectors known as gravitational wave detectors. Currently, the dominant ones that have made the bulk of the detections we've observed thus far are the LIGO detectors located here in the United States, as well as the Virgo detector in Europe, with many more detectors coming online in the near future. And so the way these detectors work is through what's called an interferometer, which is exactly shooting some laser out of some source. It reaches a beam splitter, which then splits the beam into two different directions, where it propagates outward, hits a mirror, comes back, and then recombines to give some output signal at your output for the detector. And so you'll notice that this detector is built in a plus-like form. And the reason why is exactly because of the polarizations of gravitational waves. Namely, if you were to have a gravitational wave pass through this detector, then because of the plus-like polarization, it would expand space in one direction while compressing space in the other. And so what this means is that when you send a beam of light through, if these detectors, or these arms of the detector are the same length, when the light comes back, it will recombine in such a way that you can make it so the light perfectly cancels and you don't see anything. But if there's some small discrepancy in the distances of these arms, when the light recombines, it could recombine in a constructive way, which would give rise to some detectable signal. And to help understand this principle, we can simply watch the following animation. So here you can imagine shooting some type of laser through this beam splitter, which splits out into these two cavities, which are typically 4 kilometers in length. It goes out, hits a mirror, comes back, recombines at the beam splitter, and the way the LIGO detector is configured is that when the light recombines, it recombines out of phase, which means it exactly cancels, and you don't actually see anything at the output. But if there were some difference between the sizes of these arms, which should be illustrated here in just a moment, shown here by the change in the position of these mirrors, then what you'll notice is that the phase of these beams goes in and out of phase, and the intensity of the red light increases and decreases, which gives rise to some detectable signal. And so what this means is that if a gravitational wave were to pass through this detector, the space-time would expand and contract in such a way that the light recombines in a constructive manner and give rise to some readable signal. And so, in fact, on September 14th in 2015, our understanding of reality shook when we observed one of these gravitational waves for the very first time. So here in the top row, I'm showing the exact observation we made with our detectors. Namely, this top left panel is the signal that was observed in the Hanford, Washington detector. And in the right panel, this is the signal that was observed in the Livingston, Louisiana detector, combined with the signal from the Hanford detector. And what you'll notice is that even though these detectors are completely independent, the signal that they observed is almost identical, up to some kind of noise that's due to seismic activity or an unideal scenario in your vacuum tubes. What's shown on the bottom panel is simply a reconstruction of that signal once you've filtered out the noise. And so as you can see, you have a much cleaner signal that kind of shows this oscillatory behavior. And in fact, it actually exhibits the features we would expect of a binary black hole merger. So this event was called GW 150914 for the 14th of September in 2015. And it corresponded to the merger of two binary black holes whose masses were about 30 solar masses. So an incredibly loud and actually relatively close event. But the thing I want to draw your attention to is this curve that's plotted on top of these reconstructed templates, which corresponds to this numerical relativity waveform. And so part of why this is important is because, as I said earlier, we have no guarantee that Einstein's theory of general relativity is the true theory describing gravity within our universe. And so whenever we observe one of these gravitational waves, we needed to compare it to a true solution of Einstein's equations to ensure that Einstein's theory is really correct. Unfortunately, if you take Einstein's equations, although you can solve them for a single black hole just kind of sitting there and doing nothing, as soon as you have two black holes that are orbiting around one another, it's actually impossible to work out Einstein's equations with pen and paper. And so instead, we rely on supercomputers to take Einstein's equations, set up this problem of a binary black hole coalescence, and understand what the gravitational wave emitted by such an event might look like. And so this brings us to the next part of this lecture, which is an introduction into my field of research, namely this field of numerical relativity. So what exactly is numerical relativity? Well, as I said before, numerical relativity is simply taking Einstein's equations, putting them on a computer, and letting the computer do the work for you to determine what the gravitational wave actually looks like. In practice, the way we do this is we take Einstein's equations, which although don't really care about the differences between space and time, from a numerical standpoint, we actually do decompose them into some 3 spatial dimensions and 1 temporal dimension, which is called the 3+1 form, to simply simplify our numerical evolution. And this is simply elaborated upon through this figure here, which shows some finite region of space-time with the horizontal axis corresponding to space and the vertical axis corresponding to time. So what each of these slices correspond to is some solution in your numerical relativity simulation, where the first slice is kind of your initial data. You just put the black holes at some fixed location and send them in orbit around one another. And then the subsequent slices are simply later points in time where you actually let this evolution run. The way we kind of do this is once you have Einstein's equations in this 3+1 form, there's actually 2 sets of equations that arise. One which we call the constraint equation, and one which we call the evolution equation. And so the constraint equation simply tells you what the space-time has to be at each of these slices. So for example, if I want to simulate 2 black holes with certain masses and certain spins, the constraint equation tells me what that first initial slice has to look like for my numerical evolution. The evolution equations, as their name might suggest, simply take Einstein's equations and evolve them forward in time. And the one thing to note regarding these evolution equations, which will be relevant for later on, is that it actually requires your choice of coordinates to be well motivated. In particular, although Einstein's equations don't care about what coordinate system you use, numerical simulations are more suited for certain types of coordinates and thus evolve better with the correct choice. And so this is actually one of the largest problems in numerical relativity, is figuring out what choice of coordinates we should make when running our simulations. And so at the end of the day, if you do this correctly, which was achieved for the first time in 2005, what you obtain is called the space-time metric, which simply describes that curvature we were talking about earlier. And for the purpose of this talk, we'll really just be interested in this space-time metric at some fixed radius surrounding this event. So this tells you what the curvature of space-time looks like around, say, some binary black hole merger. But now the question is, well, what is that space-time curvature here on Earth? Namely, what should we actually be detecting within our observatories? You could think that if you were to run such a simulation of some, say, binary black hole merger, you could also just include Earth in your simulation at some faraway distance and simply study the curvature at Earth. But one problem that immediately arises with this is that if you put Earth at some fixed location, this only works for one type of astrophysical event. And so really we want some kind of solution for this astrophysical event that works for all relative locations between the event and Earth. And so instead what we do to extract information about waveforms is we extract them infinitely far away from this event. And so the reason we do this is we know that if you have one of these binary black hole mergers, as the gravitational wave is being emitted, it actually falls off as 1/r, where r is the distance from this event. And so because Earth is effectively infinitely far away from the events that we see, namely a few hundred megaparsecs, what you find is that these higher order corrections, namely these terms that go as 1/r squared, are pretty much negligible. And so extracting the leading over piece, namely this piece that only matters as you take r to infinity, is sufficient for the types of detections that we're making today. And so when we extract the waveform infinitely far away from this event, it's in a regime of space-time which we call future null infinity. And so there's a few different ways we do this. Namely, the main way that most numerical relativity codes extract waveforms from their simulation is through something called extrapolation. So the way extrapolation works is pretty much shown through this diagram. So here you can imagine your spatial coordinates on the horizontal axis and your time-like coordinate on the vertical axis. And if you run your simulation, right, you obtain this space-time metric, which describes the curvature at each point in space. And so you can simply imagine taking that metric at various radial points and fitting it with some polynomial in 1 over r and 1 over r squared, and so on. And then the waveform infinitely far away should just be the coefficient you get on this 1 over r term. And so if you perform this procedure, you obtain something like the following. So here, this is the output of a numerical relativity simulation whose binary parameters, namely the parameters of the black holes that are coalescing, are the parameters that correspond to the most likely ones for that first detection, GW 150914. And so as you can see here on the horizontal axis, this is simply time with respect to the time of merger. And on the vertical axis, this is what we call the gravitational wave strain, which is simply the change in the length of the arm within the gravitational wave detector. And so here you'll see it's incredibly small. It's a factor of 10 to the negative 21. And so what this corresponds to physically is that actually for the first detection that we made, the change in distance that we measured was about 1,000 times smaller than the diameter of a proton. So it's an incredibly small feature that we're able to accurately resolve within our detectors. And so kind of the key components in the signal that I want to bring your attention to is that there's this in-spiral phase where the binary black holes are simply orbiting around one another. The strain then peaks to a peak amplitude as these black holes merge, and then after the black holes merge, you have some distorted remnant, which then rings down like a bell and gives rise to this decreasing amplitude during a phase called the ring down phase. But there's something to note regarding this extrapolation procedure. Namely, when you perform this extrapolation, we've only ever simulated some finite region of spacetime, because the larger your spacetime, the more points you have to include on your computational grid, which makes it more and more expensive. And so when you do extrapolation, you never actually solve Einstein's equations in this region outside of your system's outer boundary. And so what this means is that if there's any interesting physics that's occurring in this regime of spacetime, extrapolation isn't going to capture that. And so instead, there's a more robust procedure known as Cauchy characteristic evolution, which is what Saul mentioned earlier, that simply takes your metric data at some finite radius and performs a second evolution all the way out to future null infinity, this regime of spacetime that's infinitely far away. And so the way this works is once you have your spacetime metric, which exists at some point for all times, this serves as kind of the inner boundary for some type of evolution. And so then if you construct some slice of spacetime, which for our purposes is a slice that, say, a light-like particle would traverse, you can then treat this as an initial data problem where you have initial data on two boundaries, and you can just use Einstein's equations to evolve that slice forward in time and get waveform data infinitely far away at all times during your simulation. And so by doing so, you actually fully solve Einstein's equations. And what's a bit of a surprise is that if you perform this evolution and you compare it to the waveform you obtain from extrapolation, what you find is that this picture of gravitational waves is actually completely incorrect. And instead, what gravitational waves look like is instead something like the following. So here, the waveform I've overlaid on top of the previous is the waveform that's output by Cauchy characteristic evolution. And so what you'll notice is that although the oscillatory behavior of this waveform is very similar to the previous, you have a discrepancy at late times, which is exhibited by the fact that the strain no longer decays to zero. And this is actually a very interesting physical phenomena, which physicists have given the name gravitational wave memory. And this is really what the bulk of my thesis here at Caltech has been, namely studying this effect. And so with that, we can now transition into the theory behind this phenomena and what it corresponds to physically. Well, as I said earlier, right, when you have a gravitational wave propagating through spacetime, it causes that spacetime to expand and contract in line with the oscillations of the waveform. And because of that plus-like polarization, as one dimension expands, the other will contract. So let's go ahead and imagine we have some collection of observers surrounding some circle. So it could just be all of us in this room just standing in a circle. And let's imagine a gravitational wave passes through that circle of observers. So as that gravitational wave passes through, whenever you reach a peak or a trough of the gravitational wave, that corresponds to effectively maximal expansion and maximal contraction in a certain direction. But what the memory effect says is that because your gravitational wave strain no longer decays to zero, even after that wave has passed through the space-time, even after it's no longer present, your observers remain permanently distorted relative to their initial positions. And so what this means is that whenever a gravitational wave passes through space-time, that space-time remains permanently changed. Namely, it exhibits a memory of everything that passed through it, which is in some sense a way in which our universe never truly forgets. Now, memory is particularly interesting not only because of this fact, but also because we've never actually detected it. Currently, we only can predict it through our numerical simulations, but whenever we detect a gravitational wave in our gravitational wave detectors, the wave looks like it just decays to zero, and we don't actually capture this net change in the average value. And there's a reason for that that I'll highlight later on, but it simply highlights the fact that this is an interesting phenomenon which we still have yet to detect. Well, there's another reason why memory is interesting, and part of the reason why I fell in love with it during my time here at Caltech, which is because of its interesting connections to theoretical arguments. So within physics, one of the most famous physicists of all time is a physicist by the name of M.E. Noether. And M.E. Noether came up with this very important theorem known as Noether's theorem, which simply says that for every symmetry in a system, something is conserved. And so what that means is something like the following. So if I'm simply standing here, then the laws of physics describing me aren't changing as a function of time. And so you would say that my system is symmetric under time translations. Namely, I can just look at different points in time, and my system looks exactly the same. And so what Noether's theorem says about that is that I am actually conserving energy right now. But if the laws of physics were changing as a function of time, and I was actually radiating some of my heat, then you would find that energy isn't conserved because some of it is being radiated away. So Noether's theorem is a very powerful tool in terms of connecting symmetries of your system to certain observable quantities that your system might possess. More generally, you can understand Noether's theorem in a dynamical context as whatever charge you might measure, so say my body's temperature, is balanced by some kind of flux. So if I'm radiating heat because it's somewhat humid in this room, then you would say my temperature is changing because I am giving some kind of flux of heat away from my system. Okay, so why do we care about this, right? How does this connect to the notion of gravitational waves? Well, if we want to use Noether's theorem to kind of understand physical properties of our gravitational waves, we want to understand the symmetries that our gravitational waves possess. And to do that, we want to study the region of spacetime where these gravitational waves live, namely this region of spacetime that we call future null infinity. So this diagram that I'm showing here is what we call a Penrose diagram. Again, the spatial coordinates correspond to the horizontal axis, and the vertical axis corresponds to time. And the way we've constructed this diagram is actually normalized in such a way that if you imagine rays traveling at 45 degrees, these correspond to the trajectories of massless particles like photons or gravitational waves. And so this region of spacetime called future null infinity, you can think of as the final resting place of all gravitational radiation in some kind of system. And so now what we want to do is we want to try to study the symmetries of this region of spacetime. Because if we can understand the symmetries, we understand what kind of charge is balanced by some kind of flux, which gives us some physical insight into our gravitational waves. Now, this was some work set out on by some researchers in the 1960s. And so they actually thought this would be a fairly trivial problem. And the reason why is that if you imagine just empty space, so space with nothing in it, you can kind of already intuit what the symmetries are. Namely, if I have empty space, if I move through empty space, it still looks empty. If I rotate empty space, it's still empty. And if I move through empty space with some constant velocity, it still looks empty. And so it turns out that for empty space, there are 10 symmetries. 1 time translation, 3 space translations, 3 rotations, and 3 boosts of some constant velocity. And these are what we call the Poincare transformations. And so what these physicists thought that they would find for the symmetries of future null infinity is exactly those 10 symmetries. Because if you're infinitely far away, you're still just an empty space, so why would anything be any different? But it turns out that this is actually incorrect. And as you reach future null infinity, you actually obtain extra symmetries. And in particular, you don't just obtain 1 or 2, you obtain an infinite number of extra symmetries. And one way to see this is kind of through the following thought experiment. So imagine you have another collection of observers surrounding some kind of event, like a binary black hole merger. If these observers are in communication and know their relative positions, one observer could move to the position of any other and measure the exact same physics at the same time. But if we push these observers farther away from one another, then it takes longer and longer for them to travel to the position of any other. And in fact, if you push these observers infinitely far away from this event, they become causally disconnected, which means that they can no longer communicate with one another. And since they're no longer in communication, it means we can actually freely move each observer around their own local region infinitely far away without changing the underlying physics. And so these extra symmetries simply correspond to these translations at each point on this celestial sphere infinitely far away from our event. And they generalize the notion of a normal space translation. Because of that, we name them supertranslations. Now, the reason we care about these, which may seem like some weird theoretical experiment, is because of the following fact. They turn out to be very intimately connected to the memory effect. And one way to see this is through the following. So you can imagine, right, if you have this collection of observers on some sphere, if I send some gravitational radiation through that sphere, like some gravitational wave, the memory effect dictates that after that gravitational wave passes, the positions of those observers remain permanently changed, which is exhibited through this diagram here, where each observer has some arrow attached to it that sends it to some new location. But if memory corresponds to these differences in the relative positions of observers, that sounds very similar to these direction-dependent translations that correspond to these supertranslation symmetries. And so it turns out that if you have Noether's theorem, the memory effect is exactly one of these conserved quantities with respect to these supertranslation symmetries. And so with these symmetries, we obtain an enhanced understanding of gravitational waves, because it turns out that if you take Noether's theorem and you apply it for these supertranslation symmetries, you don't obtain the usual law that balances some kind of charge with some kind of flux. You instead obtain a new law which says that the gravitational wave strain itself is sourced by some kind of charge and some kind of flux. Namely, if I have some flux of energy reaching this celestial sphere, it creates some kind of energy density on that location, which gives rise to a net change in the spacetime as measured through the gravitational wave strain. Now, this is all pretty highly theoretical, but we can actually see this effect within our numerical relativity simulations. So previously, when I was showing images of gravitational waves, I was showing the gravitational wave that a detector might see at an individual point on this two-sphere surrounding the event. But in numerical relativity, we actually study this gravitational wave strain in a different way, because it turns out to be easier to study the strain in terms of functions that describe the sphere rather than individual points on that sphere. And so the functions we use are called spherical harmonics, and they simply correspond to pretty basic trigonometric functions that you might use to describe a sphere. So what I'm showing here, the horizontal axis is still just time, now written in the simulation coordinates. And on the vertical axis, I'm showing the gravitational wave strain, specifically a mode of the strain, a spherical harmonic mode called the 2-0 mode. And all you really need to know about this is simply the contribution to the full gravitational wave strain that corresponds to the memory effect. Now, the gray curve that I'm showing, this is the full gravitational wave strain. And the black curve corresponds to this mass charge, which is effectively just a measurement of the mass in your spacetime. Whereas this blue curve corresponds to the flux of energy emitted by your binary black hole merger. And so what you'll notice is that by using this mass or this charge and flux decomposition, we actually immediately recognize that the net change in the strain, namely the memory effect, is entirely sourced by this energy flux, which is incredibly useful for detection purposes, because if we want to detect a gravitational wave, we need to know what the memory itself looks like. And this realization here tells us exactly what to look for, namely, if we want to detect memory, we should aim to detect this permanent net change as exhibited through the energy flux. But the most interesting thing regarding memory effects, apart from this duality between memory effects and asymptotic symmetries, was actually something realized by the high energy theory community in 2014. And what they realized is that there's not simply a duality between memory effects and asymptotic symmetries. It turns out to be what we call an infrared triangle, where there's a third ingredient called soft theorems. And I won't exactly have time to go into what soft theorems entail, but these effectively describe what happens when you have a quantum system and you scatter particles and study what comes out. So you could say that soft theorems are very intimately related to the theory of quantum gravity because they describe these quantum interactions. And so because of this triangle, what memory effects tell us is that they turn out to somehow be deeply connected to quantum gravity, which means if we ever detect them, they might give some reason to believe what the quantum theory of gravity is and might even reveal some type of signature. But again, right, this is all very theoretical, and so now the question is, well, how do we actually go from theory to observation, right? We've kind of constructed this intuition behind asymptotic symmetries and realized that there's some reason to believe that memory might exhibit quantum signatures, but how do we actually observe this in practice? Well, to do this, we need to take one of our numerical relativity waveforms and simply understand how detectable it really is. And for that, we use what's called an amplitude spectral density plot. So effectively, the vertical axis here simply shows the magnitude of the strain that you might detect in your detector, and the horizontal axis is the frequency. Now, the black curve here is the full gravitational wave strain evaluated at some point on the sphere. The blue curve corresponds to these dominant, purely oscillatory modes, so the dominant mode of the strain which doesn't contain any memory. And this green curve corresponds to this energy flux, the kind of proxy we use to describe the memory effect. Now, the way you read this diagram is always with respect to certain detectors. So the yellow curve here shows the sensitivity of the LIGO detector, and the magenta curve shows the sensitivity of a future detector called Cosmic Explorer, which is about 10 times larger than LIGO. And so the way you read this diagram is that if your curve is above the detector's sensitivity, it means it's detectable. So namely, with respect to LIGO, the full strain is detectable, but really only these two modes and not the energy flux. So this means that with LIGO detectors alone, we probably won't see memory within a single event. However, if we build Cosmic Explorer, then our chances of observing memory drastically improve because now this energy flux curve is above the magenta curve. But one issue with this picture is that when we think of this binary black hole merger, if we imagine it going for all times, then you should really span all frequencies, because if the black holes are infinitely far apart, they should be spanning the low frequency regime. But as shown on this diagram here, this curve for the strain, which you see looks somewhat linear, kind of just drops off around 20 hertz. And the reason why is because I've created this plot using a finite in time numerical relativity waveform. And the reason why is because when we run our numerical relativity simulations, the longer you run it, the more expensive it is. So we typically only can run it over a finite window. And so to fix this, we need to rely on other theories used to solve Einstein's equations. And for this, we rely on what's called perturbation theory. So the general idea is that if you take a numerical relativity simulation, it's finite in length. And so to make that waveform infinitely long, we need to rely on some other method to solve Einstein's equations, which works when the black holes are largely separated. So what this diagram shows, you can really just focus on the vertical axis, which describes how far away the black holes are. So what this says is that if the black holes are about a factor of 100 apart, then your numerical relativity simulations work pretty well. But beyond 100, things become too expensive, and you instead have this alternative theory known as post-Newtonian theory, which is effectively an approximate theory. It solves Einstein's equations analytically, but only in so much as certain quantities are small, namely 1 over the separation of the black holes being some small quantity. And so if you do this, you can go from this problem of having NR waveforms that are finite in length to some infinitely long waveform which is extended by using the solution from post-Newtonian theory. And if you do this, you obtain some waveform that spans all frequencies. And I've shown exactly what this looks like for the 2-2 mode for the simulation I showed earlier. So here, the numerical waveform is shown in black. The post-Newtonian waveform is shown in blue. And as you can see, the post-Newtonian waveform extends farther back than the numerical waveform. In fact, it extends infinitely far back into the past. But so what you can imagine doing to create some combination of these two waveforms is define some window in which you'll smoothly transition from the post-Newtonian waveform to the numerical relativity waveform. And so what this infinitely long solution to Einstein's equations would be something that's post-Newtonian here, a smooth blend of post-Newtonian and numerical relativity in this intermediate regime, and then numerical relativity for the complicated components of the binary coalescence, namely the merger and the ring down. But if you look at the 2-0 spherical harmonic, namely the harmonic responsible for memory, you start to see a problem, which is that the post-Newtonian prediction and the numerical relativity prediction completely disagree. And so this is one of the problems I encountered in my thesis, which was trying to understand this discrepancy. And so the solution actually turned out to be intimately related to the theory that we discussed earlier. Namely, the issue that's being sourced here is when you run a numerical relativity simulation, you have to start it at some point in time. Namely, you have to start with the black holes at some fixed location. And because of that, the space-time doesn't have any memory about the entire past history of that binary coalescence. So what actually happens is that the post-Newtonian waveform, which does have information about the entire past history of the binary coalescence, has some non-trivial memory it's accumulated over this infinite amount of time, which the numerical simulation does not. But the insight is that because this memory effect simply corresponds to these supertranslation symmetries, all this means is that the post-Newtonian spacetime is supertranslated relative to the numerical relativity spacetime. And so what you can do is you can simply find the symmetry transformations which map your numerical relativity system to match that of the post-Newtonian system. And this is a procedure called frame fixing, which relies upon these charges that stem from Noether's theorem. And so part of why this is important is because if I were to take these two waveforms and try to hybridize them together to give something for a LIGO detector to observe, when you construct this hybrid, you obtain this unphysical feature which shouldn't really be there in the correct solution to Einstein's equation. And when this feature props up, it has some non-trivial frequency which would otherwise bias your analysis of some event and lead you to believe that you saw a certain type of astrophysical event when in reality that event was something else. But if you perform this frame fixing procedure by utilizing the information that we have from supertranslation symmetries, you go from this unphysical picture to something that looks incredibly smooth. And you can't even tell the difference anymore between the post-Newtonian waveform and the numerical relativity waveform because they lie exactly on top of each other. And so this is kind of the main problem of solving Einstein's equations, namely figuring out how to make infinitely long waveforms by running numerical relativity simulations and hybridizing them with post-Newtonian waveforms. But now the next problem is, well, once we've run one of these simulations, which can take roughly 3 months to run, how can we actually speed up this process of giving gravitational wave detectors predictions for the waves that they should see? Namely, whenever the LIGO detectors observe some kind of event and they provide the data to us, we don't want to say, great, thanks for the data, we'll get back to you in 3 months. We want to be able to give them an answer within a fraction of a minute, if not a fraction of a second. And so the way we do this is using what are called gravitational wave models, and specifically what I'll talk about is called surrogate models. Now, the way the surrogate model works in theory is you run a number of simulations at different points in parameter space. So for this example, let's consider running simulations of black holes with different mass ratios, which simply corresponds to how much heavier one black hole is relative to the other. So if we were to run these simulations, we might obtain waveforms that look something like the following. So here you can imagine running some simulation at a mass ratio of 4, a mass ratio of 1, say one at a mass ratio of 8, and finally another one at a mass ratio of 2. So now we've kind of densely sampled our parameter space. And the next thing to do is that instead of trying to model this oscillatory waveform, which is somewhat complex as a function of time, we instead want to extract certain features which are smooth as a function of time. And so one such example is simply extracting the amplitude of this gravitational wave. So if we extract the amplitudes, we can then try to fit these by picking out certain points in time which correspond to interesting features in the waveform. So for example, for each of these amplitudes, we can kind of trace through them in time and say, well, we should really model their starting value. You know, here the amplitude is starting to ramp up, so we should probably model that point, as well as this point, and also the peak, and finally, you know, maybe the final time of the waveform. And so once we've done this, we can then construct smooth functions across parameter space, which model the amplitudes at these different points in parameter space. And so with these different functions, namely these functions which describe parameter space and these functions which describe the amplitude as a function of time, we now have a way in which we can pick a new point in parameter space and exactly model what the amplitude should be. Oh, sorry. Let me get back to that. Exactly model what that amplitude should be based on the solutions we've already derived from numerical relativity. And so if you take this procedure, namely if you run Cauchy characteristic evolution on your numerical relativity waveforms, extract your waveforms that exhibit the memory effect, hybridize them with post-Newtonian waveforms through this supertranslation symmetry frame fixing, and then construct a surrogate model using the techniques that are highlighted in this animation, then you can actually construct a surrogate model and evaluate such a waveform prediction in a fraction of a second instead of 3 months. And so unfortunately, I think my code actually failed when I took your suggestions at the beginning of this talk, but we can try to remedy it during the question interview. But this, in theory, would have shown the waveform from the numbers that you gave me at the beginning of this talk. Namely, we would have had some mass ratio corresponding to how much heavier one black hole is relative to the other, namely a mass ratio of 7, I believe. The second number corresponded to the spin of that first black hole, namely the spin of the heavier one, I think 0.7. And the second number would have been the spin of the smaller black hole, which I believe was 0.3. But so here we're just showing a different example. And so what I'm showing on the left-hand side is simply different spherical harmonic modes of this waveform prediction. So here the top panel shows this oscillatory 2-2 mode, which we encountered before. The middle row corresponds to what we call the 2-1 mode, which exhibits asymmetries in your spacetime. Namely, if you have unequal masses, this will be excited. And this bottom row corresponds to the 2-0 mode, which is this mode responsible for the memory effect. And if you look at the right-hand side, this is what we obtain when we add all of these modes together and look at a single point on the 2-sphere. Namely, this is exactly what we should observe within one of our gravitational wave detectors. So the hope is that with this model and with this model of memory effects, now that we can provide gravitational wave detectors with realistic estimates of what this effect should be, they might, in principle, be able to detect it in the near future. And so with that, let me kind of briefly summarize the story we've been passing through over the past hour. Namely, we began with Einstein's theory of relativity, which we understand need not be the true theory describing gravity within our universe. It seems to work incredibly well for all of the astrophysical phenomena we've observed thus far, but again, there's no inherent reason why it has to be correct, and in fact, we know it has to be wrong because it doesn't synchronize with quantum mechanics. But we can probe this using gravitational waves, because gravitational waves probe these regimes of high curvature of large energy, which is where we expect these differences to occur. But in order to probe that, we really need solutions to Einstein's equations, which are really only feasible to obtain using numerical relativity simulations. And so with these simulations, we can then speed them up by constructing waveform models, which simply train on the data produced by these simulations and speed them up to take fractions of seconds instead of months, as I said before. But the important thing before my work here at Caltech is that all of these waveform models that gravitational wave detectors were using didn't contain memory effects because they didn't exist in numerical relativity simulations, and they also didn't account for this careful treatment of supertranslation symmetries that are needed to create infinitely long waveforms by hybridizing with other solutions to Einstein's equations. And so the hope is that now that we have these correct models of gravitational waves, we can really start to push Einstein's theory to the limits and really see when it starts to fail. In particular, we still have to detect memory, which we expect to see in the next 5 to 10 years, which is incredibly exciting because it'll happen in our lifetime. But it would also be incredibly interesting if we just never see memory, because that would mean there's something inherently wrong with our understanding of Einstein's equations, or something wrong with Einstein's equations themselves. And because of this connection between memory and asymptotic symmetries, as well as these theorems regarding quantum gravity, there's some reason to believe that if we measure memory within one of our gravitational wave detectors, it might give us some insight as to what alternative theories of gravity might be, namely theories that go beyond Einstein's theory. It may give us an understanding of what this asymptotic structure of our universe really is, because if it's different in any particular way, it might just be that the structure of our universe that we're assuming is inherently incorrect. And it might even be that certain quantum signatures from the theory of quantum gravity sourced during these extremely loud binary black hole mergers actually imparts itself on this part of a gravitational wave signal, which would be incredibly exciting because it would give us some physical observable to help understand what the theory of quantum gravity really should be. And so with that, I'd just like to thank Saul for being a wonderful advisor throughout my time here at Caltech. I'd like to thank the Simulating Extreme Spacetimes collaboration for making my research possible, as well as the Everhart Committee, the Graduate Studies Office, and the Graduate Student Council for putting together this wonderful lecture series, and also the audience for their attention. and I'm happy to take any questions that they might have. I'm also happy to fix the code and make it so that we actually see the waveform that you wanted to see. So thank you. Yeah. Right.
LIGO, I guess they have all kinds of filtering going on.
Correct.
And so, DC offset might be filtered out. So it might be impossible to see.
That's true. Yeah, so as mentioned, whenever LIGO actually measures something, there's a large amount of seismic activity that actually influences the detector. So there's a large amount of noise which influences lower frequencies. And so you can actually see this in their sensitivity curves, because as you go to low frequencies, the sensitivity just blows up. And so what these detectors actually do is that whenever they see something, they impose a hard cut at a frequency of about 20 hertz, which sometimes they push lower. And so what that means is whenever they observe a signal, any signal below 20 hertz, they just throw out. And so this memory effect, what was being called a DC effect, simply means that in theory, this permanent offset is a zero frequency effect. But the important thing to note is that it's true with these ground-based detectors, we can never observe zero frequency. We can only hope to observe that with truly falling detectors, such as detectors we might put in outer space. And so what we can do instead is, we saw earlier how this energy flux corresponds to this evolution of the memory. And so instead what we do is we say, instead of observing the zero frequency component, let's just try to observe the non-zero component of the energy flux, which we use as a proxy for the memory. And so the hope is that even though we can't observe the true DC offset, we can observe this evolution of the memory, which has some non-trivial frequency dependence. So that's at least what current experiments propose in terms of detecting memory. Namely, we just wanted to detect this green curve. Yeah, great question, though. Yeah.
The American actor Terrence Howard recently put forth some very controversial theories. I just wanted to know if you've seen it and what's your take on it?
Sorry, I don't know who that is, and I don't know what theories they proposed. Yeah. But maybe we can chat after. Yeah. Okay, should I try to fix this code then if there's no more questions? I think it should be quick. I think it shouldn't be too hard to decipher.
We may have to revoke the thesis.
I know. I tested it right before this. I don't know what could have gone wrong. Well, here, perhaps we can just do this instead. No, that's the wrong one. Yeah, unfortunately, I'm not exactly sure what's going wrong, but hopefully you can at least appreciate the idea that's exhibited through this picture. But, yeah. Yes? Right.
You have to keep track of mass in space-time. So how do you actually model the mass of, let's say, black holes? Point source, or do you distribute the mass in space-time?
Yeah, no, that's a great question too. So in our simulations, the way we measure the mass is through local measurements of the horizon, right? So whenever we run our simulation, you effectively don't need to really simulate the region of space-time inside the black holes, because you just have this kind of outer boundary problem where things should go in and nothing should come out. And so there's a certain type of mass that measures this local distortion called the Christodoulou mass. And so it effectively just comes from studying the horizon itself and extracting the mass from that quantity. It's also how we extract the spin. There's certain properties of the spin that embed themselves in a local way that we can extract using this kind of local measurement of our space-time metric. Another thing you can do, though, is that this information also propagates to future null infinity. And so if you extract the right data infinitely far away, you can actually also measure the mass and space, or the mass and spin of your space-time. But it only works when there's one black hole. So when there's one black hole, that's what we use. Otherwise, if we have two black holes, we use these local measurements. Yeah.
Yes, it's okay if you do not know this question. This is more of an engineering question. But I know at the beginning of the presentation, you kind of showed how LIGO works. I guess as like just a very basic premise.
Right.
So for CE, it's going to potentially detect energy flux that LIGO wouldn't necessarily be able to detect. Is CE going to be built in a similar premise as to LIGO, or is it going to be something completely different?
Right. So kind of what determines the frequencies that LIGO is susceptible to is the length of those arms. And so right now, the length of the arms is 4 kilometers. But in principle, if you make those arms longer, you're susceptible to lower frequencies. And so the plan with Cosmic Explorer, as well as some other future detectors that I didn't mention, is to simply make their arms longer. So for Cosmic Explorer, they're proposing to make the arms 40 kilometers in length. So they'll be 10 times as long, and thus more susceptible to these lower frequencies that are where kind of the memory effect lives for these intermediate mass binaries. But they've even proposed a LIGO-like experiment that they'll put into orbit in our outer space called the LISA experiment. And so for these, you can think that the satellites that are shooting these lasers are much, much farther apart because they're not restricted to being on Earth. And so because of that, these measure incredibly low frequencies, such as the frequencies that might be generated by supermassive black hole mergers. So there's a lot of exciting detectors that we expect to see in the next 20 years or so. Yeah.
There are no more questions. Let's give one last round of applause, please.